Welcome to Lecture 11. In this lecture, we will talk about matrix diagonalization, which is one of the interesting applications of the idea of eigenvectors and eigenvalues. Let's start with a problem that will serve as an example, and this is problem 8.4.10 in your book. The instructions for this problem, in fact, for both, we will do two problems. One will be a problem 10 here that we will do as a 2x2 matrix, and then we will do a 3x3 case. And for both of these problems, the directions are as follows. It says find an eigenbasis and diagonalize. So we'll see now exactly what that means. In problem 10, the matrix that we're interested in, we'll just give it a name. We'll call it A. And the matrix they want us to consider in that case is 1, 0, 2, negative 1. Now, the first part of what we want to do is to find all the eigenvalues and eigenvectors of A. So let's look at the eigenvalues first. Remember that to find the eigenvalues, we will set the determinant of A minus lambda I equal to 0. So we have 1 minus lambda, 0, 2, minus 1 minus lambda. That determinant is equal to 0. So we have 1 minus lambda times minus 1 minus lambda minus 2 times 0 is equal to 0. And so this tells us that we have 1 minus lambda times minus 1 minus lambda equal to 0. And therefore, we can see that the two eigenvalues for this matrix are lambda equals positive 1 and negative 1. So let's let lambda 1 equal negative 1 and lambda 2 equal positive 1. And now we want to find the associated eigenvectors. We will do this in the usual way. First of all, we will return to the definition of eigenvector. So we have A v1 is equal to lambda 1 v1, and so this gives us 1, 0, 2, negative 1, x, y is equal to negative 1, x, y. And so this gives us x equals negative x, and 2x minus y is equal to minus y. And notice that both of these equations imply that x is equal to 0. So we would choose for v1 the vector 0, 1. And now let's look at finding v2. So we have A v2 is equal to lambda 2 v2 So we get 1, 0, 2, negative 1, x, y is equal to positive 1, x, y. And so this gives us x equals x, and 2x minus y is equal to y. Now the first equation doesn't tell us anything, but the second equation, if we add y to each side, it tells us that y is equal to x. And so therefore for V2, a convenient choice is 1, 1. So now we have found all the eigenvalues and eigenvectors, and the eigenbasis that they refer to in the instructions for this problem would be the two vectors, 0, 1, 1, 1. Note that these two vectors are linearly independent, and of course together they form a basis for R2. This matrix A has all of its eigenvalues different from each other, and therefore, as we've mentioned before, in a case like that, the matrix has a complete set of eigenvectors. In other words, the number of eigenvectors n is equal to the order of the matrix. It's an n by n matrix. So it has a complete set of eigenvectors. Now, in a case like that, where a matrix has a complete set of eigenvectors, and remember that doesn't necessarily mean that there are no repeated eigenvalues. Even in some cases where we have a repeated eigenvalue, the matrix may still have a complete set of eigenvectors. And of course, if all of its eigenvalues are different, it certainly has a complete set of eigenvectors. But let's just say when a matrix has a complete set of eigenvectors, as in this case, we can diagonalize the matrix. And to see what that means, we will introduce a new matrix P, which consists it is a matrix whose columns are the eigenvectors of A. So we have 0, 1, 1, 1. And now the claim here, the claim is that P inverse AP is equal to a diagonal matrix. And in fact, in particular, the diagonal matrix that it will be equal to is the diagonal element whose diagonal is the diagonal matrix whose diagonal elements are the eigenvalues of A, and they will appear along the diagonal in the same order as the corresponding eigenvectors do in P. So in other words, since we put 0, 1 first in P, since that's the first column of P, then the first eigenvalue that will appear in D is the eigenvalue that goes with 0, 1, which is lambda 1, which is negative 1. So we will get negative 1 here. and then the eigenvalue that will appear down here in this position will be the eigenvalue that goes with 1, 1, which is positive 1. Had we chosen P to be the matrix with 1, 1 in the first column and 0, 1 in the second column, then D would be the matrix with positive 1 up here in the upper left-hand corner and negative 1 in the lower right-hand corner. But since we chose this P, then the claim is that if we will now calculate P inverse and then multiply it by A and then multiply it by P, we will get this matrix right here. So let's check that and see if it's true. Well, in order to check that, we first need to find P inverse. And we use the Gauss-Jordan method as we had before. So 0, 1, 1, 1, 1, 0, 0, 1. I will switch the first row and the second row. So we have 1, 1, 0, 1, 0, 1, 1, 0. And now add the negative of the second row to the first row. We get 1, 0, 0, 1 on the left-hand side, and on the right-hand side, when we add the negative of the second row to the first row, we get negative 1, 1, 1, 0. And now we have already obtained the identity matrix on the left-hand side, and therefore this means that P inverse is that matrix on the right-hand side, negative 1, 1, 1, 0. And now we're ready to test our claim that if we multiply P inverse by A and then by P, we will get this matrix right here. So let's check and see if that's true. Negative 1, 1, 1, 0. That's P inverse. Remember that A is 1, 0, 2, negative 1. So 1, 0, 2, negative 1. And then P is 0, 1, 1, 1. Let's see what this will give us. Okay, if we multiply the first matrix times the second one, okay, we have negative 1 times 1 is negative 1 plus 2 is positive 1. Negative 1 times 0 is 0 plus 1 times negative 1 is negative 1. 1 times 1 is 1 plus 0 times 2 is 0, so we get 1. 1 times 0 is 0 plus 0 times negative 1 is 0. So we would get this when we multiply the first matrix times the second matrix. And then we just bring the third matrix along. And now let's do this multiplication. Okay? 1 times 0 is 0, plus negative 1 is negative 1. 1 times 1 is positive 1. Negative 1 times 1 is negative 1. Positive 1, negative 1 is 0. 1 times 0 is 0. 0 times 1 is 0. 0 plus 0 is 0. And then finally, 1 times 1 is 1, plus 0 times 1 is 0, and 1 plus 0 is 1. And so sure enough, we arrive at the diagonal matrix that we predicted, whose first diagonal term is the eigenvalue associated with the eigenvector in the first column of P up here, and whose second diagonal term is the eigenvalue associated with the eigenvector in the second column of P. Now, one reason that this is handy to know about is the following. Let's take this equation here that we have now verified, at least for this case, this P inverse A P is equal to D. You might be wondering why this is useful to know about, but let me show you why it is. So let's multiply both sides of this equation by p. We will pre-multiply both sides by p and post-multiply both sides by p inverse. And so we will get A inverse is equal to p d p inverse. Again, we get that by pre-multiplying each side by p and post-multiplying each side by p inverse. Now, let's say that we wanted to take A, just as an example, let's say that we wanted to calculate A maybe to the third power. Well, that means that that's the same as P d P inverse raised to the third power, which is P d P inverse times P d P inverse times P d P inverse. But now notice that this P inverse P there and the P inverse P there are both equal to I. So we have P d I d I d P inverse. But of course d times I is d, so we have that A cubed is equal to P d cubed P inverse. Now, why is this interesting to know about? Well, okay, P, remember, is just 0, 1, 1, 1. 0, 1, 1, 1. D is just this matrix right here, -1 in the top term, upper left-hand corner, +1 in the lower right-hand corner, and 0 otherwise. When we cube that, we just get -1 cubed, 0, 0, +1 cubed. And then finally, P inverse, we found, is -1, 1, 1, 0. The point here is that it was when you have a diagonal matrix and you want to raise it to some power, that's the same as just raising each term along the diagonal to that power. On the other hand, for A cubed, we have to multiply A by itself 3 times. Now you might say, well, that's not really any more work than what we have here, because we have three matrices multiplied together. And you would be right that if we were only trying to calculate A, say maybe to the third power, that this approach would not save us any time. But suppose now that we wanted to calculate A to maybe the 27th power. That would take a lot of work. But if we use this approach, we would still have just 0, 1, 1, 1 here, and then D raised to the 27th power, which is very easy to calculate. It would just be -1 to the 27th, 0, 0, +1 to the 27th, and then we'd have -1, 1, 1, 0. So we would still only have to multiply 3 matrices together to calculate A to the 27th power, whereas if we calculated it directly, we'd have to multiply the matrix A times itself 27 times, which would be an awful lot of work. So this is a very attractive application of the idea of diagonalization. And of course, I'll just leave it to you if you wish. You can go ahead. Of course, -1 cubed is -1, +1 cubed is +1. So it would be easy to multiply this out and to verify that it is indeed equal to A cubed. So let's do one more example of this, but with a higher dimensional case, just to make sure that this is all clear. And this next problem will be a little bit more involved, but I think it's worth it to see one more example. So we'll look at problem 8.4.14. Now the directions are the same as for the problem that we just did. The matrix that we have in this case, we'll again call it A, and that's -5, -6, 6, -9, -8, 12, -12, -12, 16, and again, we want to find an eigenbasis, and we want to diagonalize this matrix, and they are telling us that one eigenvalue is -2. And that will be helpful because, as you know, since this is a 3 by 3 matrix, we will end up with a third degree characteristic polynomial. And the characteristic equation will be a cubic equation, which can be challenging to solve, but now that we know one root, it will be trivial. So let's see how this goes. Okay, when we set the determinant of a minus lambda I equal to 0, well, let's see, we get -5 minus lambda, -6, 6, -9, -8 minus lambda, 12, -12, -12, 16 minus lambda is equal to 0. And I encourage you, I very strongly encourage you, you have enough information to do this problem, so I strongly encourage you to stop the video and try to do this yourselves, and then come back and see if you have the same answer that we get here. Okay, so I hope that you did try that and that it went well for you. But now to work it out here on the video, since we don't have any zeros in the determinant, there's not any really preferred way to evaluate the determinant, so I'll just go across the first row. So we'll have -5 minus lambda times -8 minus lambda, 12 minus 12, 16 minus lambda. Then we'll have minus a -6. Remember, this minus, the minus sign here in front of the -6, this minus sign here comes in from the checkerboard pattern that we use for the coefficients. So we have a minus of a -6. And then we will have -9, 12, -12, 16 minus lambda. And then finally we will have +6 times -9 minus 8 minus lambda, -12 minus 12. And that will be equal to 0. So now this gives us -5 minus lambda times, okay, when we multiply -8 minus lambda times 16 minus lambda, we will get lambda squared. And then we will also have a -8 times negative lambda, so that's +8 lambda minus 16 lambda, so we have -8 lambda. And then finally, -8 times 16 is -80 and minus 48, so minus 128. And then from, we also need to remember this other term. We have a minus a negative 12 times 12, so minus a negative 144, so that will give us plus a positive 144. Plus 6, I'm taking negative of the negative, so we get plus 6, times, here we will have 9 lambda, minus 144, plus 144. And then finally, plus 6 times 9 times 12 is 90, and 18, so 108, minus okay, I guess I'll do this in the following way. So we have 108 minus the product of negative 12 and minus 8 minus lambda. And that is 0. Okay, so now this is the same thing as minus lambda plus 5 times lambda squared minus 8 lambda plus 16. Plus 54 lambda plus 6 times 108, and then we have a negative times a negative. Both notice that this is negative 8, negative lambda, negative 12. So we could make all those negatives into a positive, and we get minus 96 and minus 12 lambda. And this is equal to 0. So now we're going to get minus lambda cubed minus 8 lambda squared plus 16 lambda plus 5 lambda squared minus 40 lambda plus 80 plus 54 lambda plus 6 times 8 minus 12 lambda equals 0. And this should be not 8, but 12. 12 minus 12 lambda, because 108 minus 96 will be 12. Okay, so now we get minus of lambda cubed minus 3 lambda squared minus 24 lambda plus 80 plus 54 lambda plus 72 minus 72 lambda is equal to 0. So minus lambda cubed plus 3 lambda squared plus 24 lambda plus 54 lambda out here. It gives us plus 78 lambda. Oops, we also have a minus 72 lambda here, so 78 lambda minus 72 lambda will actually give us 6 lambda. So 6 lambda. And then finally, we have minus 80 and positive 72, so that's minus 8 equals 0. So unless we have made an error, this is the characteristic equation for this matrix. Now remember that we were given a hint here, which is lambda 1 equals negative 2. And let's just check this to see that it would work. Okay, if we took negative 2 and cube it, we would get negative 8, and the negative of negative 8 would be positive 8, and positive 8 minus 8 would, okay, that would give us 0. So what if we plug in negative 2 into the rest of this? Well, negative 2 times 6 would be negative 12, and negative 2 squared would be 4 times 3 is positive 12. So sure enough, negative 2 is a root of this equation. So this gives us confidence that this equation is correct. So now we want to find the other two roots of the equation, and the way we'll do this is the following. We'll say, okay, minus, we'll use synthetic division just as we did the other day in a recent lecture. So we take minus lambda cubed plus 3 lambda squared plus 6 lambda minus 8 and divide that by lambda plus 2 since the root is negative 2. And so let's see what will happen. Okay, we'll get minus lambda squared. That will give us minus lambda cubed minus 2 lambda squared. And now change the sign and add, and we will get 5 lambda squared plus 6 lambda minus 8. So now we'll say plus 5 lambda. That will give us 5 lambda squared plus 10 lambda. Again, change the sign and add. We get minus 4 lambda minus 8. And now we have minus 4, which will give us minus 4 lambda minus 8, and change the sign and add, and sure enough we get 0. That's great. And so what this means is that minus lambda cubed plus 3 lambda squared plus 6 lambda minus 8 equals 0, which was our characteristic equation. That can be written as lambda plus 2 times minus lambda squared plus 5 lambda minus 4. It can be factored in this way. And so now we'll be able to find the other two eigenvalues for this matrix. What I would do now is I would take out a negative sign, so simply because I like the leading coefficient to be positive 1 rather than negative 1. So lambda squared minus 5 lambda plus 4. And if you wish to put the negative sign out front, you can, but you can also take it over to the other side, and of course negative 0 is the same as 0. And now, if you wish, you can use the quadratic formula to find the roots of this quadratic term, but it's easy to see that this will factor into lambda minus 4 times lambda minus 1. And so just as easy as that, we have all of the eigenvalues. So the eigenvalues are lambda equals negative 2, 4, and 1. And I'll label these in an increasing order. So lambda 1 is negative 2, lambda 2 is 1, and lambda 3 is 4. So there are the eigenvalues of this matrix. And now let's find the associated eigenvectors. So for V1, okay, we will have A V1 equals lambda 1 V1. And so this is minus 5, minus 6, 6, negative 9, negative 8, 12, minus 12, minus 12, 16, x, y, z equals negative 2, x, y, z. So this gives us minus 5x minus 6y plus 6z equals negative 2x, minus 9x minus 8y plus 12z equals negative 2y, and minus 12x minus 12y plus 16z equals negative 2z. So the first equation will become minus 3x minus 6y plus 6z equals 0. The next one becomes minus 9x minus 6y plus 12z equals 0. And the final one becomes minus 12x minus 12y plus 18z equals 0. And now I think that what I would recommend doing now, before we go to Gauss elimination, is to get these coefficients smaller. I would divide the top equation by negative 3 to get x plus 2y minus 2z equals 0. I would divide the second equation also by negative 3 to get 3x plus 2y minus 4z equals 0. And then finally divide the last equation by negative 6 to get 2x plus 2y minus 3z equals 0. Those steps were not necessary. I'm just trying to simplify as much as possible. And now I would go to Gauss elimination. So we have 1, 2, negative 2, 3, 2, negative 4, 2, 2, negative 3, 0, 0, 0. And we add, let's see, add negative 3 times the first row to the second row to give us 0. Negative 3 times 2 is negative 6, and 2 is negative 4. Negative 3 times negative 2 is positive 6. Positive 6 and negative 4 is positive 2. Add negative 2 times the first row to the last row. So negative 2 and 2 is 0. Negative 2 times 2 is negative 4, and 2 is negative 2. Negative 2 times negative 2 is 4, minus 3 is 1. 0, 0. And now, well, this is getting pretty easy to see already, but I'll just go ahead. Let's maybe switch this. Well, let's divide the second row by 2. So we get 1, 2, negative 2, 0, 0, negative 2, 1, 0, 0, negative 2, 1, 0. And so now we add negative of the second row to the final row, and we'll get 1, 2, negative 2, 0, 0, negative 2, 1, 0, 0, 0, 0, 0. So as we expect, there are infinitely many solutions, which is what we wanted, because we know that once we find an eigenvector associated with a particular eigenvalue, that any non-zero multiple of that eigenvector is also an eigenvector associated with that eigenvalue. So now let's see what these final equations give us. We have x plus 2y minus 2z is 0, and negative 2y plus z equals 0. And this second equation implies that z is equal to 2y. And if we substitute that into the first equation, then we have x plus 2y minus 2 times 2y equals 0, or x plus 2y minus 4y is equal to 0, or x minus 2y is 0, which tells us x equals 2y. And so finally, we conclude that x equals z equals 2y, and therefore a suitable choice for V1 would be 1 for y and 2 for both x and z. And if you wish, we can check that. Check 1, 2, negative 2, 3, 2, negative 4, 2, 2, negative 3, times 2, 1, 2. And let's see, we would get 2 plus 2 is 4. Well, let's see, 2, 1, 2. Oh, wait. No. Our matrix is, I wrote down the wrong matrix here. Our matrix A is negative 5, negative 6, 6, negative 5, negative 6, 6, negative 9, negative 8, 12, negative 12, negative 12, 16. So now if we multiply that matrix times this V1, what do we get? Okay, negative 5 times 2 is negative 10, and negative 6 is negative 16, and 12 is negative 4. Negative 18 and negative 8 is negative 26, and 24 is negative 2. Negative 24 and negative 12 is negative 36, and 32 would be negative 4. And sure enough, that is negative 2 times 2, 1, 2. So indeed, the vector 2, 1, 2 is an eigenvector of this matrix with associated eigenvalue of negative 2. Now let's find V2. So we have negative 5, negative 6, 6, negative 9, negative 8, 12, negative 12, negative 12, 16, x, y, z is equal to lambda 2 times v2, and lambda 2, recall, is 1. So we have 1 times x, y, z. And so this gives us minus 5x minus 6y plus 6z is equal to x, minus 9x minus 8y plus 12z equals y, and minus 12x minus 12y plus 16z equals z. Okay, so minus 4x minus 6y plus 6z is 0. Minus 9x actually, no, this should be minus 6x here. When we subtract x from each side, we should get minus 6x. So minus 6x minus 6y plus 6z equals 0. And then when we subtract y, we get minus 9x minus 9y plus 12z equals 0. And finally, when we subtract z from the last one, we get minus 12x minus 12y minus 17z, plus 15z plus 15z equals 0. And right away, we see something interesting here. The first equation could be written if we divide through by 6, and we would conclude that z is equal to x plus y. Now, you don't have to solve this in this way, but I'm just trying to show you a fast way to do it. So again, we come to that conclusion by dividing through by 6 and then taking the x and y terms over to the other side. Now, if we next will substitute that into the second equation, notice what happens. The second equation could be written as minus 9 times x plus y plus 12z equals 0, but x plus y is equal to z. So this is minus 9z plus 12z equals 0, which says 3z equals 0, which says z equals 0. So z is equal to 0, and remember x plus y is equal to z, so x plus y equals 0, which means y equals minus x. So an appropriate choice for v2 is 1, negative 1, 0. And since we checked our first eigenvector, let's go ahead and check this one as well. So we would get negative 5, negative 6, 6, negative 9, negative 8, 12, negative 12, negative 12, 16, times 1, negative 1, 0. And let's see what that gives us. We get negative 5 and positive 6 is 1. Negative 9 and positive 8 is negative 1. And negative 12 and 12 is 0, which sure enough is 1 times negative 1, 1, negative 1, 0. So this verifies that this vector, v2, is indeed an eigenvector of this matrix with associated eigenvalue of 1. And now finally, we want to find v3. And so we get minus 5, minus 6, 6, minus 9, minus 8, 12, minus 12, minus 12, 16, x, y, z is equal to lambda 3 times x, y, z, and lambda 3, recall, is 4. So we have 4 x, y, z. So we have minus 5, minus 6, 6, minus 9, minus 8, 12, minus 12, minus 12, 16, x, y, z. Oh, no point in repeating all that. Let me go ahead and just write out the equations. So we'll get minus 5x minus 6y plus 6z equals 4x, minus 9x minus 8y plus 12z equals 4y, and minus 12x minus 12y plus 16z equals 4z. And now let's work on each one of these. We get minus 9x minus 6y plus 6z equals 0. Minus 9x minus 12y plus 12z equals 0. And then finally minus 12x minus 12y plus 12z equals 0. And once again, it looks like we can pull a little trick here to make this easier for ourselves. Notice that the first equation implies that if we take 9x over to the other side of the equation, we get 9x is equal to 6z minus 6y. But the second equation implies that 9x is equal to 12z minus 12y. And therefore 6z minus 6y is equal to 12z minus 12y, and so y must equal z, and x must be 0. And so appropriate choice for V3 would be 0, 1, 1. And let's check that. Negative 5, negative 6, 6, negative 9, negative 8, 12, negative 12, negative 12, 16, 0, 1, 1. And that will give us 0, 4, 4, which is 4 times 0, 1, 1. And that's exactly what we expect. So indeed, the vector V3 here, 0, 1, 1, is indeed an eigenvector of this matrix with associated eigenvalue of 4. So now that we have our eigenvectors, we can form the matrix P. The first column of P will be the first eigenvector of A, so that will be 2, 1, 2. The second column of P will be the second eigenvector, which is 1, negative 1, 0. And the third column of P will be the third eigenvector, which is 0, 1, 1. If you use the Gauss-Jordan method to find P inverse, you will find that P inverse is given by the following 1, 1, negative 1, negative 1, negative 2, 2, negative 2, negative 2, 3, and then if you check this, P inverse AP will indeed give you a diagonal matrix D whose first diagonal term is lambda 1. Remember, lambda 1 up here was negative 2. So we have negative 2, zero, 0, 0, 0, 0, 0. The second diagonal term is lambda 2, which is 1. And the third diagonal term is lambda 3, which is 4. And you can check that for yourselves. And the eigenbasis here is simply the eigenvectors 2, 1, 2, 1, negative 1, 0, 0, 1, 1. And so that's how we would do this kind of a problem for a 3x3 matrix. So now let's look at a couple of problems. For 11.1, I would like you to do problem 8.4.9, and for problem 11.2, try problem 8.4.13. Now that second one is a 3x3 case, but there are, because of the zeros in the matrix, it will be considerably simpler than the problem we just did. So those are the two problems, and that will finish lecture 11. And so that's it, and good luck.